Hi, in last video we learned one of the lossless compression technique, that is Huffman coding. In Huffman coding we learned that we have to read string first, then we find frequency of the symbols, arrange them in descending order of their frequency, and then we design a Huffman tree. But many times there may be no prior knowledge of data. For example, multimedia data like live audio. In such cases, our Huffman coding algorithm will fail. So, there is need of adaptive Huffman coding. Here are some flaws in Huffman coding. It requires prior knowledge of information. Mostly in multimedia applications, future data is unknown before arriving. For example, live audio or videos. But in adaptive Huffman coding, statistics are gathered and updated dynamically as data stream arrives. Adaptive Huffman coding is useful in multimedia, so we do not require prior knowledge of data in adaptive Huffman coding. A simple procedure of encoding and decoding is given here. In encoding, while end of file is not reached, we have to fetch the character, encode it, and update the Huffman tree. Similarly, in decoder, while end of file is not reached, decode the character, give output, and then update the Huffman tree. While designing a Huffman tree, that is adaptive Huffman tree, we have to consider two properties. That is, one of them is sibling property, and second one that we have to arrange the nodes of the adaptive Huffman tree in non-decreasing order. Let's see one example of this. Here in figure A, we have a Huffman tree containing the symbols A, B, C, D and E. The frequency of each symbol is given in front of them. Now consider one more A arrives, means we are receiving second A now. We already have A and we are receiving the second A. So the frequency of letter A is now become 1 plus 1, 2. That is greater than B, C and D. So we have to swap A with B, C or D. But for avoiding multiple swaps, we will just swap A and D. That is the farthest element. After swapping A and D, we will get a new tree as shown in figure B. Now consider that we again receive A. That will be the third A. So now the frequency of letter A will become 2 plus 1, that is 3. This step will be more involving and will be solved in C1, C2 and C3. Now the frequency of A 2 plus 1, 3 is greater than the parent node level node, that is fifth node. So we have to swap A and fifth node. But fifth node is non-leaf node. So the subtree with node D, B and root node 5 swapped as whole with A3. Now we can see the swap condition in figure C2. The tree is swapped with A as shown by this arrow, and the tree will look like this. Now the frequency of 7th node will become 5 plus 1, that is 6, which is greater than node 8, that is 5. So we have to again swap node 7 and 8. So after swapping we will get the tree that is shown in C3. In this, the sibling property of adaptive Huffman tree is maintained. Let's see one more example. Note that the node numbering corresponds to the order in which nodes are combined by Huffman's algorithm. First nodes 1 and 2, then nodes 3 and 4. Now consider this tree in which we have 11 nodes. We have symbols A, B, C, D, E and F here. And now one more B we received. But we already have B. So now the frequency of B will increase by 1. That will become 4. And if we update the weights now, so it will give us 4 plus 2 6, 6 plus 5 11, 11 plus 11 22 and 22 plus 11 that is 33. But here we can see that the sibling property and the non-decreasing weight property of nodes are violated. So we have to use some different way. And this is no more a Huffman tree. Now let's see the another way. Here, when B will arrive in first phase, we will not shift B or we will not increase the frequency of B. We will just shift or simply say swap node 4 and 5. Then we will swap node 8 and 9, as when the frequency of B will change, it will become 4. So 2 plus 4 will become 6, 6 plus 6 will become 12. This value will be greater than the parent level value, that is 11. So we have to swap nodes 9 and node 8. After this swap, now we have a Huffman tree and root is rich. So we will stop here. Now we will increase frequency of B in second phase. That will become 4. 4 plus 2 6. 6 plus 6 12 and 12 plus 21 that is 33. Now we will assign 0 to the left side and 1 to the right side. And according to this, we can find the compressed code using adaptive Huffman tree. Thank you.